Hello, 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 hello.
just make sure all their presentations are in and everything. So
sounds good.
I got
Give
two
me
of
a few
them in.
minutes to then. So this is their final throw, the red line interviews. They should have all of our comments addressed.
Yeah.
And Natalie and I hung out for like an hour after you guys. We all hung out
today?
Yeah. She wanted to know what she missed, so she called me. And she's checking on whether she can get a babysitter to come on the 8th.
Right. Carl England said he couldn't come.
Oh, shoot.
So we might just postpone things.
13th. Oh, okay. Just let.
Should I do IDX or IDX guest? Oh, no, never conference.
Let's see. Do IDX for now.
Okay. Right. Running YouTube.
And just type in IDX Google platform.
Oh, here.
Actually,
Good. Here.
yeah, right there.
Here. Just go here.
Yeah.
These work. Live now.
The way I've set it up, it should be able to look at the presenter as well.
Oh, nice.
As well as the, so it's a little different interface.
Yeah, it's great.
Yeah, so now somebody can click back and forth. It is dependent upon the user to go back and forth, but I think it's actually.
Now, is there a place for the users? It would be really great. Oh my gosh. I have a snap coming up. I have like a bug.
I got one too, and I've never had it on a Mac before.
But it's in my Chrome.
Oh, really?
Oh, really?
Because I don't get these. I don't have this weird stuff going on in Safari.
Okay.
Oh.
Interesting.
It's freaking me out.
Maybe something picked up at the conference. They're all free.
Oh, well, this might be just on the YouTube page. But okay, what would be awesome is if in here there would be opportunity for
Questions or something like that. Okay.
And is this password protected on YouTube, or is it open to the whole world?
It's open to the whole world. Nobody knows about it though. So.
Okay. Just gonna type in like IDX or find it really quick.
Oh, that's so funny. It's a little delayed.
Yeah, it's definitely delayed, but whoever's watching it can.
Yeah.
Because your training videos are all on there too.
Yes. Okay. So.
So I should turn it off though, because that would be really.
Yeah. Just.
Oh, so Natalie just provided comment in the Word documents today. She said she's trying to do something. So other things she
Oh, good.
wanted to tell you guys. But if you're pushing the 8, let her know as soon as possible.
So England's not available the 8th.
What about Vic?
How about the 13th? US?
I didn't check on that all.
Okay.
I haven't responded to him yet.
Okay.
Not Vic there. Wolcott there?
Oh, how about Wolcott? He's not. If you interact with him much, I don't feel like he's breathed down our back very much. Is he just like written us off, or are we doing a good job?
Yeah, who knows? I mean.
Yeah, he's like.
I can ask for a review at the end of last year. It's kind of conflicting. It's like you guys take too many assumptions, move forward too quickly without, and it's like. But then, on the other hand,
We have a class.
Hello,
so,
is that really
learning
objective?
that was one of the things. And so, but on the other hand, he was like, you guys don't take enough initiative to just go out and do stuff. Like, so.
Weird. I would have liked to have been there for that.
Yeah.
Purchasing.
Or I pulled him aside that last day.
The Kevlar.
Yeah.
So, I think we just move forward as best we know how. My only gripe a little bit is just like interaction with Sphinx and the other Mars and stuff like that. Like unless there's leverage there, I don't know if we're actually gonna do that.
They don't reply.
Sphinx great in person. Like,
Yeah.
I just haven't had great email and correspondence with them.
Exactly.
So yeah, I think. And
of
IDEX,
books.
IDEX really lags on a lot of the other stuff that we do, so, say TEA or something like
Right.
that, or getting in with Cosmo, you know, like, there's so much of this insider stuff that's going on, which is fine, but
Yeah.
we can't be expected to provide assets for that.
You know what we need though, is we need, sorry, I gotta go, we need a simplified TEA spreadsheet that is student level,
Yeah.
that they can complete, because the one from Speak that Natalie has is,
Yeah.
I'm not kidding you, it has like 500 tabs in it or something like that.
Which is outrageous.
Yeah, yeah, you guys have to meet Tiffany, well, cause she's sworn to sheriff. It is so tough. I think everything is so tough. Everything that I got to is way up the hill.
Oh, yeah.
With your email correspondence. Wouldn't that be great?
I don't see anything in there that I wouldn't want people to know about. So.
How's Bill McLaughlin doing, you know?
No, I was gonna have a get together with him yet. I saw him in the end of July, early August.
Jay.
Yeah, his third set of treatment, and I just talked to, I think, Ed Crombie had the CSS over on Friday.
Oh, nice.
So I was talking to Sharp, she said that he broke that marriage. But that he seems to be doing pretty well.
Oh, good.
So yeah.
Did you see Micah Brooks' baby yet?
Uh-huh.
You did? Does it have a name yet?
Eleanor. Eleanor and Alberta Sky.
Really? They're gonna call her Ellen. Eleanor Alberta Sky Lowry?
Yeah.
So 40.
Yeah.
Oh. That's interesting. And you have to think, would she be under the Alberta Sky?
Yeah, right. There you go.
Let's read in Bell. Mr. Lowry. That's funny. So that means Becky Couch probably got her.
Yeah, probably. I wish, yeah, but that, I do feel like
My clients personally wouldn't Panera clients. You know what internal business or like business to business is?
but you and I think maybe, at the end of this week, I'll try to get my head around the concept of the meeting, and then look over what you have on your table, and, maybe we could just, and then I could lay out something that, like basically what I heard as, suggested IDX outputs for years 4 and 5.
Okay.
And then maybe we can pull something together, send it out to Vic or Carl, like, hey, can we just all get together for half an hour and make sure that this is what I kind of heard business is needed, that direction, because like Tom King was saying, we need perspective, business perspective for potential investors.
Oh, no, of
course we don't. But is that something we need or want to do as an outside perspective? And if so, IDEX could take a piece of that and feed it to something else. We're not going to do the whole thing, but we could do a little piece. Which is where I'm coming from with those. This is what a self-team is. If you have big plans, these are the opportunities that would be helpful to have on our own, whatever, right? Like,
Yeah.
Anyways, that's just where I'm headed with it.
Well, one of the things that I think that they don't do a very good job of is cross-disciplinary and like interdisciplinary connections to all of the resources here at WSU. Like, Speak was complaining that nobody's looking at, $5 million worth of ash every year, or cost of $5 million.
Right.
I'm like, well, that's really simple. You could get with Shelley Presley and have a senior in chemical engineering look at that in the SURE program for a summer.
Yeah.
Connect the dots. And then when Carter Cox was working on the market stuff for the activated carbon, which I think is grossly overrated, but
Right.
huge
We
number.
may acknowledge that.
Yeah, and he come in a ballot statement and all those? Why don't they like talk to one another?
Yeah.
Or vice versa, any of the other colleges and universities that are involved in NARA also have those same kind of
Right.
business resources.
You guys saw that link when we sent it?
I can't even get online right now, so
Let me see.
I don't know. Oh, now I'm online.
Review form, I got it.
You got it?
Yep.
Michelle, you need it?
Did you send it to my IDX?
I'll just send it to you.
Okay. Pacific Northwest faculty.
Got it. Just gonna.
Called review form. Okay.
I feel like there needs to be a speed dating session, for lack of better terminology, with the other segments of all the universities involved in there. Like now there's a FAA center here. Carl, are you involved with that?
I had an option B, and I chose to do it this month, so that's very nice.
And you didn't get bought out from teaching?
I did to a certain degree. But that's good. So. Teaching 2 projects.
Instead of 5.
Well, I normally teach 6 a year. And this year I'm just teaching 4.
One of which is IDX, and then one other one.
Yeah, I teach a surveying class and then another computer application class. Teaching my like students. Keep me busy.
With no grader and no teaching assistant?
No, I have TAs. I have labs as well, so I go through. Try to streamline, make high efficiency.
Okay.
Ben said he would look over the assignment Wednesday morning for us as well. Just I've been having him kind of go through since he's been on the student side. It's really helpful to have him.
That's great. ENW faculty.
Oh, if you go to your email, I got it.
They're awesome graphics.
I think it's pre-treatment put together a pretty sweet graphic for their flow.
Wirecast. Yeah.
That's how I'm streaming this time.
Oh. Trying out something new?
Well, I'm trying it. There's a computer here that's presenting streaming the screen, and then I'm also streaming the presenter, so they can see themselves actually present in front of the screen.
Nice.
So people can go back and forth. If they want to read text, they can get the text, and if they want to see the other.
Will they get feedback, or I mean, audio feedback from that, or no?
From this year, like, I mean, when they actually look on it on YouTube, they can get all the audio there.
Okay. That's kind of neat, the dual functionality.
Yeah, I'm trying to. It was a little bit of a mess from last time, so I'm just trying to make it better.
I wonder if we should give them wireless mics, like TED Talk kind.
I do have one. The problem I was looking at is just going through the switching it back and forth. It's just kind of a nightmare. So I put this thing up here for now, which is our.
Yeah, that's a great microphone. That works out really well.
Yeah.
Carl, are Hangouts automatically recorded somewhere in our hard drive?
If you select them as a live hangout, they are. Or meaning on air kind of thing. So.
So like if Natalie and I had a hangout earlier, that's like a separate button that we click?
It wouldn't. Yeah. So when you start the hangout, you have to make sure it's a live hangout. So.
Okay.
So it's not by default.
Gotcha.
Why does that have to do with mine?
Yeah. We were just asking that the other day, like, oh, what if
check out this one.
Wow, I'm so impressed. That's a
Great.
that
Isn't
has
that
to be
amazing?
Sydney.
No, this was actually Ian.
Oh, really?
Incredible. He did a great job.
That's
So, isn't that amazing?
And it's all citations and everything. Yeah, I'm really impressed.
So just building on how it builds, I think.
Yeah.
And you know, it gives numbers here, gives where high energy amounts are going in. I mean, that's exactly what we're looking for. So
That's a wonderful job.
that's Ian's. That's Ian. I mean, Ian's top game. So
The next bit.
yeah, I think he's got a little more filter than Vince. Vince will just dive into every detail. Like, and Vince is great. Don't get me wrong. Like, Vince is my 99 percentile, but Ian's got an ability to kind of know what he can read within, like, what you're asking for him.
Nice.
And he can make good quality decisions in this.
Okay.
So I think we are good to go.
More of an independent worker. We didn't make them take the social test.
I know, I thought about that the other day too.
I actually wanted to do that partway in.
Okay.
I think if they get a feel for each other, and then after the first assignment we do it, I like to actually do it on Wednesday. Then they've seen each other work.
Nice.
Now we take them and go, oh, I get it.
Oh, yeah, that's great.
Okay, so you still plan on doing it? That's
Yeah.
awesome. Cool. Cool. Do you know that Ivan Easton is from Detroit?
No.
Isn't that hilarious? It's so funny. Need to unsequence local drive because my computer is like blowing up. Charles spoke to me at the conference and he has this kind of like aloofness about his personality. It's like very off-putting kind of way. Oh, is your hair different? Oh, yes, it's good. Is one to say whether it's good or not. He's like, I can't figure out what's different about you. And I just wore my hair curly like naturally for 20 years. Like, oh, well, pretty smooth. You're full of skills.
So you're gonna have 6 people, or?
Hi. Oh,
Yeah,
it's
the whole
just
class
the
is
three.
coming.
Yeah, the whole class is coming, but we'll take
Yeah.
your paper stuff.
And the foreign dignitaries
Yeah.
too.
I think still said 6.
So this is your. Oh, it's the 3 of you.
We have 3 more.
Yeah, there's a few people that didn't show up.
Is that
Okay,
the other
well,
three
I
we'll
was hoping to
keep
get a
them
few
here.
extra people.
And we'll pass them out.
They're online technically.
Okay. They'll be online.
Kara
too.
Ford,
Yeah, we'll just
pass
pass them out.
with us. So.
We have 2 other reviewers coming in. Cause she's where now?
I was saying there's 3 other groups.
So,
Other girls.
where should we stand ideally?
Is Vince gonna be here today?
No, he has a nephew.
Oh, that's where we're being
Oh,
recorded.
no, Vince.
Like right about here. Let's give a presentation.
Yeah.
So if you guys, I would encourage you guys to stand either side the way you're in the middle, the lighting on you changes. So yeah, something like that. That'd be great. So that'd be great.
You gonna make me stand over here all alone?
Actually, you should probably do this.
Yeah, so somebody can run the clicker. We guys got a couple people up there. So the way we have this with the presentation is it'll be live streamed, and people can click on whether or not they want to see the presentation or see through this one. They can see you guys interact with you guys do points and stuff. Yeah.
Do you have a remote clicker, or is it just
I tried for the life of me. They say you can connect these things, and it worked for me once, and then it did not. So I tried for about half an hour. So we got arrow keys, all the basics. So.
And the mouse works too if you want to take the mouse up.
Yeah.
Just left click the mouse.
Or you can get another quicker. Was that?
Yeah, I was gonna say I have my wireless mouse on.
Does the arrow keys work? Is that mouse name kind of shows up?
All right, guys. So real important, especially for those of you guys. Right after this assignment, we're going to be combining teams. So you guys will be in 2 teams essentially, the depot team and the conversion team. So part of this is really to get you guys up to speed with what the other team's been doing. I know you know to a certain degree, but please pay attention to that portion of it. And whenever you guys are ready, go ahead and get started.
Yeah.
All right. Welcome. We're the NARA pre-conversion team here. My name is Matt Jarrett. I'm a civil engineer at Washington State University.
I'm Brian Hansen. I'm a bioenergy engineer from University of Idaho.
And I'm Stephen Keith. I am a civil engineer from Washington State University.
So to begin with, we think it's important that we understand where we are in the whole NARA supply chain, from where we're getting the initial feedstock and where we're finally going to a biojet. We've circled our region, and while it's important that we take a look at everything happening in this specific phase, it's also important to realize what comes before and what's after, because that's going to affect our decisions that we make later on. But not only are we limited to this whole geography of the phases, we're also taking a look at the geography of our region. The location of biomass and the location of rural communities are going to be very important when we go to our site selection.
So we start off needing woody biomass. We will collect this biomass in the forms of slash piles from previous logging operations or construction and demolition products, or residues. The next step is to sort and remove debris. The slash will have leaves, bark, and or needles, depending on the species or variety of tree available. And construction and demolition biomass will have nails and other metal residuals that need to be removed. From there, we need to choose to either chip and refine the density of the biomass or transport it raw. Another option that we researched or found in our research was mobile torrefaction. It's a process that involves cooking the wood at 200 to 300 degrees Celsius. It increases the grindability of the wood product, which inherently will help us increase the energy density of the biomass, and also increases the hydrophobicity, making it harder for the biomass to absorb water, increasing long-term storage capabilities, and then we would send the either chipped torrefied wood or pelletized torrefied product to pre-treatment. If we step back to more common practices, we could either chip on site and send that to pre-treatment, or send it to a hammer mill and create wood flour, create bales out of the slash piles and ship them to either a localized site or a depot, or transport the slash piles just as raw biomass and not process it at all. Then we can pelletize the wood flour or mill the chips from the bale process and pelletize it and send both of them to the pre-treatment facilities. This is kind of an overview of the whole process, where it's all connected. There are a lot of options. No one option seems optimal for any site. So each site has to be studied in depth individually, and even different locations at specific sites will require different methods.
All right, and we're just going to tie it back into how this phase of the NARA project, it's all about the physical transformation of the wood, taking it from this initial state and condensing it down. It's really dependent on the energy of our wood. That's what we're going to be looking at. That's a huge variable, because we want that energy as dense as we can, because it's such an initially low value source. And then another thing we're also going to consider is the outputs. What are we going to be getting out of our node? How's that going to affect down the line? How's that going to help the economies of the local communities? First of all, we're going to consider the inputs. Start at the beginning. We need to know our feedstock. And that comes back to that map of our region. We need to know which trees are accessible, where these slash piles are, what are going to be the efficient ways to get that out of there. Additionally, that ties in with the regional assets. What infrastructure is nearby? What do we have available for use? And as I mentioned earlier, the rural economies. NARA's one of NARA's chief goals is establish rural economies and help build these communities that could really use the economic development. And then we've also, as Stephen illustrated earlier, has talked about mobile conversion, doing chipping on site, and maybe alleviating some of those high transportation costs.
All right. In the comminution of the material, which means breaking it down into a smaller average size particle, is very important in the next step. It helps densify the product, and it gives a material that the pretreatment and subsequent steps will be able to use. It is very important that there is clean sources of wood. The materials can cause, if there is contamination such as sand and rocks or human particles like nails or wires and things, these can cause problems in the not only damaging the machines but also kind of just like having unclean source of fuel for the next step. We've been looking at different milling efficiencies, and we found that chippers are ranging between 30 and 80% more productive than a grinder. It's found that shearing wood takes a lot less energy than grinding it up and pulverizing it. And if we can find that our output is better to be just in chip form compared to ground flour, we can reduce a lot of our costs and energy consumption. Another big critical part is the energy use of these machines. It has shown that fuel consumption is 30 to 75% greater for grinders compared to chippers, and electric grinders are significantly cheaper, but in their consumption of energy. Instead of using diesel, you're able to use local electricity. Another thing that we're looking at also is drying the chips. If we are going to be pelletizing them, it's very important that they are at a correct moisture, so we can use different tumblers and other methods to dry the material.
The next step is our outputs. And it's important to consider the energy density of our product. If you're transporting raw biomass via bin trucks throughout a forested region, your efficiency is really low. You have a lot of empty space in each truck, and for a high diesel cost. So if we're able to either chip at the sites or transport the raw biomass a short distance where we can chip, grind, torrefy, or process otherwise, we can increase the density, load it into larger trucks, larger than bin trucks, tractor trailers, double trailers, whatever is the most feasible option for the road conditions. We increase the amount of mass we transport per unit diesel. The water content is then also really important to keep in mind. The more water or water moisture in our biomass, the more weight that we're transporting with that diesel that doesn't really contribute to the biojet project. But it's also important to consider the next steps in pretreatment, because depending on the pretreatment process, a higher water content actually makes their cost cheaper. So if we spend more in pre-conversion, we might save more in pretreatment. It depends on our methods. Pellet and other byproduct marketability. It's important to keep in mind where we're going to be working in these rural communities, where we're helping them out by giving them stable jobs, but we're also producing a marketable product. Chips, wood chips, bark, like beauty bark, and pellets are common products used to heat homes and generate electricity via steam plants. And if you are able to create the infrastructure to produce these products and sell them to steam plants, to schools who are capable of generating their own steam-powered electricity, you are able to open up that market now and use that infrastructure so that when the research or methods are refined to a point where the biojet project is more viable versus petroleum products, you could, I mean, half of the infrastructure is there. It's just a couple more steps, and it's done.
And I'd like to bring it back to where pre-conversion fits in the NAR goals. First, our first goal is creating a biojet fuel. If we can create a biojet fuel, that being our main goal, we really need to make sure that every step that we do along the way is as efficient and cheap as possible, like in the process of making it. Along the way, we do create many byproducts, as Stephen was talking about, of having pellets or other fuels that we could sell to local businesses, or looking at bark as a byproduct that could be sold to other places. We have rural economic development. These are going to be located in towns and places that have a high worker, I gotta say, they have, man, I'm spacing out. High unemployment rate. I grew up in a town that was a lumber industry town, and lately a lot of the mills have been shutting down. This created a huge unemployment rate with a lot of people that are interested in the industry, and they would be happy to go back and work for the mills. We also look at how we tie in with all of the other groups and the 4-state project with the pre-conversion, understanding where our site development is going to be, understanding what our outputs are going to be for the next steps along the way. And while all doing this, we'll be increasing the literacy of the local people, having them understand what we're doing and knowing that we are doing a good thing, that we are creating jobs, that we are creating a carbon neutral fuel, that we are creating a better life for all of us.
There are references.
Thank you very much.
All right, thanks guys. So we'll just run through all the presentations, guys, and at the end we'll kind of pick up with some details.
My name is Ian Smith. I'm a student here in civil engineering at Washington State University.
I'm Cody Lane, and I'm also a student here as a civil engineer at Washington State University.
And our part of the project, the NARA project, is the pretreatment and hydrolysis, and we're gonna low down on the whole process.
So kind of the process is going to start with getting a biomass, which is kind of like the wood feedstock that we kind of mentioned earlier, and then from there it'll go through our pretreatment process using the mild bisulfite protocol. And from that, you'll go through the hydrolysis process where the sugars will be broken down, and then we'll go into depth with, and then from there it'll get fermentated, and then it can become refined biofuel.
Yeah, Northwest Advanced Renewables Alliance is a company that gives investors sustainable technologies for regional problems. So every part of this process will try to be sustainable, and will have high efficiencies. And so our feedstock that we have, our material that we're taking out of the forest, is going to be forest residuals and slash piles, pretty much waste products from other forest industries. And so the breakdown of that feedstock is cellulose, hemicellulose, and lignin. Cellulose is, we have percentages up there, but roughly about 40% of the overall structure. Hemicellulose is about 20%, and lignin is about 25 to 30%. And there's extractives, but the extractives aren't really pertinent to our process overall, and so we won't be focusing on too much of how those extractives go out through the process. But the breakdown on each one of those components, the three main components of cellulose, hemicellulose, and lignin, are in cellulose is glucose, and that's going to be our main focus, is going to be on getting that glucose extracted out of the cellulose. And the hemicellulose is those 5 different sugar molecules, and those will be turned into a biofuel. And the lignin is mainly made out of alcohols, which makes it a good fuel source for burning or whatnot. And what we have right here is plant cell, and then that goes into the plant cell structure and the cellulose structure. And what we have here on the left side, my left side, your right, will be the cellulose structure, and each one of those individual blocks will be glucose. And then that string together, it's free flowing out there, will be the sugar chain, and then the block of all the sugar chains will be the cellulose. And inside this middle structure right here, you can see the yellow part, which is the cellulose structure, which is the core, and then surrounded by that is the hemicellulose, and then outside that is the lignin. And the strongest bonds in that structure are going to be the lignin to the cellulose, and the weakest bond is the hemicellulose to the cellulose and the hemicellulose to lignin. So our pretreatment, the mild bisulfite protocol, takes advantage of that weak bond between the hemicellulose and the other components. And so that's really what the pretreatment protocol will be focusing on.
Okay, so with the beginning of the pretreatment process, kind of as you mentioned, we're trying to take that weak bond between the hemicellulose, the cellulose, and the cellulose and lignin, and break them apart. So we're going to start with like forest residuals, which is our wood chips, kind of feedstock, the biomass. But combining with that, we're going to get the calcium bisulfate, and that is created with sulfur and calcium carbonate being combined, and this is heated along with water. And the water actually will be kind of recycled from the plant, as you'll later see in the diagram, and then this will be heated in the boiler and also used as energy. So the steam, the calcium bisulfate, and the biomass go into this mild bisulfate protocol process where it's very acidic. It's like a pH of less than 2, and this is where the hemicellulose is kind of separated from. And then going on to the next process, which Ian's about to talk about, you'll have the lignin and the cellulose kind of going as a substrate.
So throughout the literature on pretreatments and different types of pretreatments, we got 3 main factors that go into a good pretreatment. And so the first one will be making the cellulose accessible to the enzymes and the enzymatic hydrolysis, which we'll get to later. And the second is creating usable forms of hemicellulose and lignin. And the third is it economical and is it robust? So is it, for the amount of energy you're putting in, are you getting a good product out of it? And is it robust? Is it getting the materials out of the NAR feedstock that you want, mainly the sugars? So is it getting all those sugars out in an accessible form? And so after the mild bisulfite protocol, you have 2 different outputs. One is the solid substrate, and it comprises of the cellulose and the lignin. Those are the 2 main things. There's a little bit of hemicellulose left over in that, and then the spent sulfite liquor, which is the sulfite pretreatment combined with the hemicellulose and the acid-soluble lignin. And so we'll start with the solid substrate. First, we'll go through a mechanical size reduction, and that's something we'll have to work with the pre-conversion team because one of the main parts that makes this pretreatment economical is that it softens up the wood because it's held at a temperature about 140 to 190 degrees Celsius for about 25 to 30 minutes, and it softens up the material, and it deconstructs some of the structure, and it reduces the amount of energy you need to put in the mechanical size reduction. So in the NAR research into this pretreatment, they used a shredder, and they blow the chips through the shredder to shred it. Just makes kind of a long fibrous kind of material. But there's many different opportunities to reduce the size in different ways, as you saw in the pre-conversion team. So then that will be shredded, the reduced particle size, and that also increases the accessibility of the cellulose, mainly because the contact area between the enzymes and the cellulose will be increased because there's increased surface area on the cellulose. And so that'll go into washing, where the rest of the SSL, spent sulfite liquor, will be washed off the solid substrate, and then that will be added down to the original spent sulfite liquor. And that clean substrate contains the majority of the glucan, which is not quite glucose yet, it's still in the cellular structure. And so it's about 90% of the overall glucan that was in the wood chips, about 80% of the lignin, and 3 to 5% of the hemicellulose. And the reason that the ranges are so wide comes from the different types of woods that we going in, as well as different regions will have different types of woods. So I mean hardwoods, softwoods. It's kind of a combination of all those different types of woods. And so now to focus on the spent sulfite liquor, that'll be mainly the hemicellulose that was stripped off of the plant cell structure. And so it's about 90% of all the hemicellulose, 20% of all the lignin, and 10% of the glucose. And so that spent sulfite liquor will go into an evaporator, will be condensed about 50% of its original volume, and then the steam that comes off that evaporator will go back into the process of putting it into the water and then the boiler, or it could go directly straight to the pretreatment process, depending on how constant that process is.
And going off of like the different makeup of the glucan, the lignin, and the hemicellulose, at the NAR conference they talked about how right now they've done a lot of the research has been with Douglas fir, and about 60% of the biomass is Douglas fir, but that's combined with a lot of other stuff, and I think that's going to kind of come with site selection, which will further go into, I think, the next couple weeks, but it just kind of is going to be based off where we think it's going to be economical for this project. So going with what we said in the diagram we talked about earlier, the plant cell structure that has, after it's gone through the pretreatment process and the substrate and the spent sulfite liquor is kind of in this, it's now has been altered, so the enzymes are going to be able to, so the weak bond of hemicellulose is now gone, and it's in the spent sulfite liquor, the majority of it is, and now in this, the substrate you're going to have the lignin and cellulose, and in this next process, which we're about to show you, the enzymes are going to be able to utilize that bond and the lack of hemicellulose being there and further separate them.
Yeah. And another point to make on how economical this, or how more economical this process is in the combination of the calcium carbonate and the sulfur dioxide, the reaction between those two of a strong acid and a weak base creates a decent amount of energy that can be put into the boiler. So it dramatically reduces the amount of energy that has to be put into the boiler, whether it be natural gas or any similar biomass or electric. So that's another benefit of this malolactic bisulfite protocol.
So from there, you got the clean substrate, and like we talked about how the water is kind of constantly being recycled, is now an input for the enzymatic hydrolysis, and that's going to be combined with cellulase and lime, and it's a little bit differently than they used at the paper mill that we went to, because their lime I think is used more at the beginning of the process versus at the end, and that's because ours is more acidic, and so you're going to have those two input along with the water and the clean substrate, and you're going to have outputs of the glucose, which once was glucan, is now the usable glucose that we're trying to use, and before it goes in the fermentation process, and this is about 85 to 95%. You're going to have lignin, which is about 75 to 85%, and then you're going to have just a small amount of hemicellulose, which is about 3 to 5%, and that's going to kind of go and combine with the condensed SSL, which is about 50% condensed now, and those two are going to be combined with the fermentation process.
And to further go into detail of what the enzymatic hydrolysis is doing, in the cellulase enzyme, there's really kind of three components of that cellulase. And the first one will cut one of the free chain ends, and so now you have one side of the chain, of the sugar chain, connected to the hemicellulose, and the other one's free floating. The second enzyme will go in and cut the other one out, so now you have one whole chain floating out. And that's what you can see right here. The whole chain is floating outside of it, and that's the second step. And then the third step is to cut those bonds between those. So you go from cellulose, which is glucan, to glucose, which is each one of those individual blocks.
And then in this fermentation process, which I believe the next group is going to kind of go into depth with, you're going to have three of the main outputs are going to be refinable biofuel, which is the main component of that is the glucose. And this has a lot of commercial uses, but this is kind of the main focus of this project is that glucose. And so that refinable biofuel can be also used kind of in a paper mill and some textile fibers. Also, you have the lignin, which we kind of have discovered that plants can use that also as a biofuel, so we could use that as an energy source to sustainably energize this plant. But it can also be used in other kind of industries, as a dispersing agent. It can be used kind of for road dust control, and it can also be used kind of as activated carbon. So there's a lot of different uses for lignin as in commercial uses if we had that as a byproduct. And the past group kind of mentioned that. And so then we also have the lignosulfonate, which he's going to kind of talk about.
Yeah, lignosulfonate has a decent sized market right now for as a concrete additive to increase the plasticity and the workability of the concrete, also reducing the amount of water that you need to put in, so increase the strength of concrete. So it's a very good product for concrete. And also on the note of the lignin is there's now an emerging market on polymerizing the lignin and making it to more like a plastic, and as a replacement of kind of the fossil fuels that they use as plastics. So it's another way of increasing sustainability. Lignin is a wood product, and therefore could be, instead of putting it into a landfill, it could be burned or whatnot after you're done with your toy, something like that.
That was it.
Thank you.
Whenever you guys are ready.
Hi, my name is Anna Martin.
I'm Christian Williams.
We are student civil engineers working with NARA. Our NARA's main goal includes taking woody biomass and converting it into jet fuel. This is the region specifically that we're working in. Includes Washington, Idaho, Oregon, and Montana. We want to complete this goal for a few different reasons. The woody biomass, it's a cleaner form of energy from a waste that would normally just be burned or left behind. It's also a renewable form of energy.
This is the supply chain that NARA wants to utilize to create jet fuel. There's many important steps to it, and it starts with collecting biomass from the forest and breaking it down into chips or pellets, and then sending it off to pretreatment, which they'll introduce a solution that breaks down the structure of it. So the lignin, which is the structure, that creates the structure, and it separates the lignin from the carbohydrates, which are then sent through a process called hydrolysis, which breaks it down into simple sugars, those simple sugars are then sent through fermentation, which introduces a yeast or a biocatalyst that produces isobutanol, and that can then be turned into a kerosene, which can be combined with petroleum and used in jet fuel. And our node that we were tasked to research is fermentation, and we'll discuss that with you in our presentation today. So going over the basics of what fermentation is, it's pretty simple from a broad spectrum overview. It's combined with a yeast, bacteria, or an engineered biocatalyst in a bioreactor, which is a large tank, and it's set at a set temperature or pressure, and it goes through a chemical reaction to produce isobutanol along with other byproducts. Now, the image here shows that just how simple it is from a large view of it, from sugars to isobutanol, and it also shows how similar the process is for fermentation into isobutanol as well as into ethanol.
But just to take you through our inputs and outputs of our conversion process, we take the simple sugars that's from the woody biomass, and depending on plant to plant or research facility to research facility, they would add a biocatalyst enzyme, a yeast or bacteria, and some kind of nutrient. There's still a lot of research going on what's the best to put into the process. Nobody really agrees. GIVO, for example, they use a bioengineered bacteria and some nutrients. Their nutrients, they discussed a little bit with us, are still being in the process of being researched, and they're getting better and better at it as time goes on. Another input to the process is water, which is one of the things that when it comes out of the bioreactor, it can be recycled. A lot of times it comes out clean enough just to be directly recycled into the fermentation process. Sometimes you would also require some kind of water purification to clean that water up a little bit before you put it back into the bioreactor. We'll discuss capital costs of that later. Another one of the inputs is some kind of agitation. Yeast, if it just sits there, will only ferment what's around it, so it's important that we're mixing it up. Some of the other renewable things that come out of our bioreactor is methanol, which we need to put an arrow back into our bioreactor, butanol derivatives, and ethanol. In a lot of cases, they make the yeast more comfortable, but in some other cases, they could kill off yeast. It all depends on what you're putting in. GIVO, for example, really likes to reuse the methanol, butanol derivatives, and ethanol because their specific form of yeast tends to like it. It tends to like to create the isobutanol off of it. Other times, you have to completely take it out and restart it in the process to try to get it into isobutanol, which is another one of our outputs. That's what we're trying to go for. That's what you get to make jet fuel. Residual carbon products is a super important output that you get out of this process. Makes us a lot of money. Talk more about that later. And then we get, no matter what kind of fermentation you use, you'll always get carbon dioxide and heat. So more specifically into this bioreactor business, we did a lot of research into kind of what looks to be the best process right now. 5 bioreactors in series seems to be the most beneficial. It can handle 2,205 US tons per day of the solid material, the woody biomass. And that would produce 61 million gallons of isobutanol per year. The 5 bioreactors that we would have would operate at 82 degrees Fahrenheit, and the entire process would take about 1.5 days. As the kind of slurry of material is moving through these bioreactors, outputs are being constantly strained, and then kind of the undesirable outputs are being re-put into the next bioreactor to try to get it to turn into isobutanol. In every bioreactor, about 86% of your sugar is going to turn into isobutanol. In the end process, we'll only have about 1% of sugar loss, which is a really great turnaround when we're taking these simple sugars and trying to turn them into isobutanol. For every 1 gram of sugar used, we're going to need about 20 milligrams of enzyme, biocatalyst, yeast, that kind of thing in the process. More about costs. The batch reactor, not necessarily in our process, but is needed before the bioreactors in order for the fermentation process to work. That costs about $18.3 million. All 5 bioreactors are going to cost $31.2 million. Wastewater plant, optional. It depends on your process. Sometimes it'll come out clean enough. The wastewater plant won't be needed. That's about $49.4 million. It's our most expensive infrastructure. Distillation and solids recovery, that's the part that you're taking out of the bioreactors that you're getting the isobutanol out and you're getting the residual carbon products out so we can continue to use them or turn them into something else and sell them.
So the next table shows basically our energy costs for each step of the process. And we found that the total energy consumption for the fermentation process is 116 gigacalories per hour. And based off of EIG.gov, we found a total cost for this process of about $193,000 per cycle, so every 1.5 days. But what's important to note is that these numbers are based off of ethanol production because it was difficult for us to find any numbers for isobutanol because it is such a new process.
It costs about 20 cents a gallon to put it in a more realistic term to produce the isobutanol in the fermentation process. Some different types of yeast that we ran into a lot. There's still being researched, but these were kind of the ones we thought were worth noting.
So the first yeast we found is Saccharomyces cerevisiae. It's really common in many industries for fermentation, such as bread making and wine making. However, for our process, some of the cons are that it produces a low yield of isobutanol, and it's also slow in production, which could increase our costs and the time needed for fermentation. Another thing is that it also requires a special the wood requires a special pre-treatment, and this is true for many yeasts and bacteria used, because the pre-treatment type affects the amount of sugars you have and what types of sugars you have, which really affects isobutanol production.
The next type is Ammonium mobilis. It's a type of yeast that has a very high cellulistic sugar uptake. It really likes to take the sugars and convert it into isobutanol, and it takes less time. And also it yields more alcohol, I guess I should say. You don't need to introduce additional oxygen into the process, and that's another very expensive thing. It means more infrastructure. It means you're also going to have to find a way to introduce more oxygen. And it has a really high ethanol tolerance. That's important because a lot of different kinds of yeasts will die in the presence of ethanol. So it takes a lot of effort and energy to continuously strain out that ethanol. The bad thing about this type of yeast is it does favor ethanol production, and when we're trying to get isobutanol, that's not necessarily the best thing.
A bacteria that we found that is really favored as one of the most likely to be used in commercial fermentation is Escherichia coli or E. coli. It's really common and easy to obtain, and something good about it is that it breaks down our sugars well and produces a good yield of isobutanol. However, it's easily inhibited by the isobutanol, which means that once the isobutanol is produced, it becomes toxic to the yeast that are producing it, so it won't produce as much. So that means it's going to need constant separation from the slurry during fermentation. It's also susceptible to bacteriophages, which is viruses that can spread throughout the strain.
The last type that I want to talk about is Clostridium cellulopoticum. It's the very first type of bioengineer kind of strand that researchers played with to try and create this isobutanol. It originally came from decaying grass. It set the stage for companies like Gibo in order to bioengineer their own type of bug, I guess you could call it, to turn the yeast into isobutanol. The bad thing about it is it didn't do the best job. It's only a prototype, but it's important because it was the very first one.
And something important to note about these yeasts is that Gibo is still, or in our talks with Gibo, we learned that they're still researching which yeasts work best. So they're starting small scale production and fermentation for isobutanol, and they're putting each yeast under certain conditions and measurements of how much yeast goes in. And they're taking the best ones and slowly ramping up the scale to production.
We talked a little bit about our outputs. These are the markets that we identified. The isobutanol, most important one, we can take it and turn it into jet.
Another byproduct is fermentation carbon products, which can be turned into activated carbon. This is a very profitable byproduct because it can be used for many things, such as water filtration, gas masks. It can also be used in medicine, which we need to add, which will be very profitable.
Two other output markets, water and ethanol. Those both come out of the fermentation process. Depending on what kind of fermentation you're using, a lot of times you could just directly input them right back into the fermentation process and try to get them to output isobutanol. It's very important that we're able to reuse the water. Water's an expensive, high cost. And ethanol, another way it could be reused is it could be strained out and also could provide energy for our plant. Water can also be reused as a type of cleaner if we need to be cleaning off our machines, that kind of thing.
Some other byproducts are butanol derivatives and methanol, and both can be reused in the fermentation process because it helps our yeast grow. And butanol can be reused as a biofuel as well, although it will be less energy efficient and have a lower octane rating than isobutanol. And methanol can also be used for antifreeze and solvent.
The last two outputs are heat and carbon dioxide, which are the natural process of any fermentation.
Thank you for your time.
Arrow keys. Back and forth. Okay. Okay, when you go to ready.
All right, so my name is Kyle Stevens, and I'm a civil engineer here at Washington State University.
And I'm Sydney Diekman. I'm also a civil engineer here at Washington State.
All right, and our group was tasked, or part of the NAR group, tasked to research the refinery aspect of this project. All right, so NARA's main goal was to develop a plan for introducing a renewable source of biojet fuel into the market. And the four-state region that they've been focusing on was Washington, Oregon, Montana, and Idaho. And what do those all have in common? Trees. So our plan was to take forest residuals and chop them up, and then we would loosen up the molecules during pretreatment, take out the sugars, and then we undergo fermentation to create isobutanol, and then we take that isobutanol, refine it, and turn it into isoparaffinic kerosene, which is our jet fuel, which we'll refer to as IPK. And the node we were focusing on during this presentation is refinery. All right, so the process overview. There's four main processes that happen during the refinery node. And those are dehydration, where we take the isobutanol feed stream and take out all the water. Then there's oligomerization, where we increase the length of these carbon chains. And then there's hydrogenation, where we saturate the carbon chains with hydrogen. And distillation, where we separate out all our products and byproducts so that we can either sell them, reuse them, or combust them. And first up is dehydration.
Okay, so the first step is dehydration. Initially, we had a hard time finding sources that actually talked about the dehydration of isobutanol, but after talking to representatives of GEVO at the annual meeting, they indicated that they have tried to develop their processes around oil refining processes. And in this case, they said that dehydration was similar to semi-regenerative catalytic reforming in the oil refining process. So, I mean, at the end of the day, they're removing the water, but how they do this is they run the feed stream from fermentation through a fixed heater to heat it up so that it will react with fixed bed catalyst, which will probably be like a platinum metal over a silica alumina surface area, and that'll start getting the water out, but it's a slow process. They have to run it through 3 fixed bed catalyst reactors and heat it up in between each each time. These reactors will get larger as they go because the process slows as your isobutanol is getting converted to isobutene. And then after this, it'll go through a gas separator where the hydrogen gas is siphoned off, and that'll actually be used in the hydrogenation stage, so they're able to, utilize the resources there. Additionally, the products will be condensed and sent into a stabilizer, which is otherwise known as a fractionating column in the oil refining process, where they take advantage of boiling points of the products basically to separate out the heavier molecules and the lighter ones. And from this, they'll get the isobutylene stream and send that off to oligomerization.
All right. And then, so the main purpose of oligomerization is to increase the length of these carbon chains that we get. So the length of an isobutylene carbon chain is C4, so 4 carbon atoms, and we're trying to turn that into either C8, C12, or C16, and then even some C20. C20 is used for like J5, higher end jet fuels, and then the main focus of what we're going to be getting is C12. So during this process, we have to take the gas from dehydration, and then we run it over a fixed bed acid catalyst. And the catalyst has to be activated around like 300, 400 degrees Celsius, which will then start the process, will start the reaction. And then this reaction is exothermic, so we actually make heat. You'll see there's a heat output, which we might be able to use for other processes. They talked about heating up water to make it easier for some other processes in this. So, so we have the catalyst and we run it over the catalyst, and then these carbon chains the C4s will group together into C8, C12, C16s. And when they do that, they're increasing their molecular weight, and they're also increasing their energy density. And the reason we want to do that is so that we have a higher energy density that is more comparable to IPK, more comparable to jet fuel, so that we can actually blend it with that. And we want to have a 50-50 blend in the end. And part of the reason for that is if we just sold it primarily as IPK and not to mix with jet fuel, we would have to actually make certain engines for our fuel, and that would be a huge process and cost lots of money. So we're going for a 50-50 blend. And so we increase the carbon or energy density of this, and then some of the gas that goes through this catalytic reactor will be cycled back through, because if it's still a gas after that, that means it hasn't reacted high enough energy density or molecular weight to be a liquid throughout this process. And then we send off all the liquid to hydrogenation. And the purpose of hydrogenation is to saturate these carbon chains with hydrogen. So there is a lot of double bonds between carbon atoms that were created during the oligomerization process. And we want to basically remove all the double bonds and make them just single bonds with hydrogen. And again, the reason that we do this is so that we can increase the energy density to make it more comparable to jet fuel. And the way that we do this is we'll take that liquid and we'll run it over a catalyst. Again, it has to be activated. And then it will react with the hydrogen, and we'll ship that off out to distillation. And then one thing to note about the catalysts is that they have to be refurbished every 6 to 24 months. And basically you just burn off all the excess that has been attached to these catalysts, so that you can create more surface area for the gas and liquid to run over it and react.
The problem is that when the hydrocarbons are going through the catalyst bed at high temperatures, it forms what's called coke, and it covers up the catalyst, and so it reduces the surface area that can react with the feed stream coming through. So you just have to burn that off every once in a while to regenerate the catalyst bed. So the next step is distillation, and this was exactly the same as in oil refining. So it's actually a pretty neat process. It takes advantage of the different boiling points of different molecules. So heavier, more dense molecules have higher boiling points. It takes a really large temperature to get it to turn into a vapor. Well, at this point we have isoparaffinic kerosene. That is the heaviest molecule that comes out of this process. So basically, to separate it out from all the other things that have been carried through and produced throughout the feed stream, you get a steam reboiler, which can be powered by natural gas, and so that's going to be an input here. And the steam heats up the liquid at the bottom, and it goes through a fractionating column, which is separated by levels with bubble cap trays. What happens is the vapor comes up through like a sieve hole, and then it hits a cap, which forces it down into the liquid that's on that level. If the vapor is the same as that liquid, it will condense when it goes through that liquid and become part of it. But if it's still If it's still lighter than that liquid, it will just continue on through the vapor up to the next level. And this way you're able to siphon off all the different molecules that share very similar boiling points, because the temperature decreases as the vapors rise through the columns. So that's how they're able to do this. And any excess gas waste products, they're able to burn off in what's called a gas flare, which also requires water for steam, because otherwise the gas that comes out, the smoke cloud is too black and gritty. So they add water to that. And at the end of it, you're going to siphon off your IPK and start blending it with jet fuel. So there are some potential markets for byproducts and outputs that are coming along this process. The isobutanol alone can be used as a lacquer or as a varnish. Isooctane is a good fuel on its own. You can blend it as a fuel additive. Isobutylene can be oligomerized into polyisobutylene, which is the same thing as butyl rubber, which has a lot of applications. It's the only gas-permeable rubber that exists, so it's used for the inner linings of tires and basketballs and applications like that. Or it can be used alone as a chewing gum ingredient. Methanol has has a list of applications as well, but an interesting one that I found was that it can be used in wastewater treatment processes for denitrification. Because if you get too much nitrogen coming out in your waste stream, then you increase the BOD of the water and you start to deplete the oxygen in the surrounding environments. The activated carbon is one of the big money makers for this product. It comes out and it's used for things like water purification mostly, but it can also absorb odors and bad tastes in other drinks. It can be used to purify air, and there's a big market for activated carbon.
And then so far as numbers go, we were able to compare it a little bit to the petroleum refinery, and we figured out that it was approximately 14 kilowatt hours per barrel, and then an average oil refinery will make about 18,000 barrels of oil a day, which will cost about $25,000 a day for electricity costs and operating this. And that's it. Do we have any questions?